Hi.
Good luck.
So it's a great pleasure to introduce Laura Geatti, speaking on N-invariant geometry of Hermitian symmetric spaces.
Okay, thank you. It was a bit hard to start. Okay. So this is joint work with my colleague Andrea Iannuzzi from Rome Tor Vergata. So I will begin by, what's next? I don't see the next one. How do I go to the next one? Okay. So I will introduce first the problem we deal with, and then try to introduce the statements, and hopefully have some time also to discuss the methods. So the problems we are discussing are these. If we have a domain in a complex manifold, one of the questions is to determine the envelope of holomorphy of D. So the largest set where all holomorphic functions on D extend. In general, if M is a reasonable manifold, the envelope of holomorphy of D is a Stein-Riemann domain spread over M. It means that we have a diagram like we see now. We have D, we have an embedding into M, you have an holomorphic embedding into its envelope of holomorphy, and then we have a projection Q, which is a local biholomorphism. So the first question is to ask whether Q is injective, and if Q is injective, to determine D hat. A problem like this is very difficult to solve in general. So often, I mean, unless there are symmetries, we are in a very special situation. If, for instance, a Lie group G acts on M and D is an invariant domain, then all the objects inherit, also D hat inherits a G action. The maps I, J, and Q are G equivariant. And so the questions now can be reformulated as follows. We have a complex manifold with a Lie group acting, and we are looking for the envelopes of holomorphy of G invariant domains in M. We try to characterize G invariant Stein domains in M. And in general, we are also interested in G invariant plurisubharmonic functions. A classical example that we could keep in mind is the case of subdomains in Cn. We have Cn, we have the group G of real translations. G is Rn, acts on Cn by sending Z into Z plus B. B is an element in Rn. And the G invariant domains in this case are the subdomains. So the classical Bochner tube theorem says that the domain D is Stein, so it's domain of holomorphy, if and only if the base omega is convex. The envelope of holomorphy is univalent or schlicht, as you want, so it means that the projection Q is injective. And in this case, then the envelope of holomorphy of D is the smallest Stein domains containing it. So it is indeed the convex hull of D. Moreover, when D is a Stein subdomain, then we have that there is a one-to-one correspondence between G invariant plurisubharmonic functions on D and convex function on omega, which makes sense because D is Steins and omega is convex. So this is an important example for us because we are trying to generalize these statements to the setting of Hermitian symmetric spaces of non-compact type. So we have G mod K, it's a non-compact Hermitian symmetric space. We assume it's irreducible of rank R. So we can assume that G is a simple non-compact Lie group, K is a maximal compact subgroup, and we fix a reference point, a base point, x0. So now if we fix an Iwasawa decomposition of G, means that every element of G can be written as the product of an element in N, which is a maximal unipotent subgroup. A is a maximal split Cartan subgroup in G, no, R-dimensional, and K is the maximal compact subgroup. So we fix an Iwasawa decomposition, and then, for instance, we have that the group N, which is a maximal unipotent subgroup of G, acts by left translations of G mod K, and these transformations are by holomorphisms of G mod K. The subgroup NA acts simply transitively on G mod K because of this Iwasawa decomposition. And also we have that every n orbit meets this set, this A times x0, the orbit of x0 under A, transversally and in a single point. This is just consequences of the Iwasawa decomposition of G. So the conclusion is that the real R-dimensional subset A times x0, so the orbit of the base point under this split Cartan subgroup, encodes all the N-invariant information on G mod K. Okay, so if we want to obtain an Iwasawa decomposition of G, we take the Lie algebra, we have a Cartan decomposition of G, we take a maximal abelian subalgebra in P, and which is R-dimensional, because our space is of rank R. So we have the restricted root decomposition of G. We take N, the sum of the positive root spaces. And so we have N is the exponential group generated, the group generated by that algebra N, and A is also the exponential of A. K is maximal compact in G. Okay. The simplest example is the upper half plane. Here G is SL2R, and N is the subgroup of upper triangular matrices with ones on the diagonal. A is this, the diagonal matrices, and K is orthogonal subgroup. And you see the N orbits in this case are just the horizontal lines. And the A times x0, the orbit of this group A, is the imaginary part of the plane. So this is the situation in the case of the upper half plane. If we take another rank 1 space, the ball, for instance, this is the bounded model, no, the ball itself. And then we see that in this case, the A orbit of the reference point is this red line, the horizontal line, and the N orbits in this realization are the orospheres tangent to the point 1. So here, this is the orbit situation, the N action on the ball. Okay, now we consider a very special feature of the group of isometries G of a Hermitian symmetric space of non-compact type. We have that the Lie algebra of G contains a subalgebra which is a direct sum of R copies of SL2R, and these are commuting pairwise. So then we have to this Lie algebra there correspond a subgroup of G. This subgroup contains A, and one has that the R orbit the orbit of the base point under this group, which is roughly a product of R copies of SL2R, pairwise commuting, is a closed R-dimensional complex submanifold of the symmetric space, which is biholomorphic to R copies of the upper half plane. It is a kind of polydisk theorem, but with this time we have a poly upper half plane. So this product of upper half planes, it's like a thick slice for the N action. So let's see. Okay. Now later I will have some examples. So we know that if we have a Hermitian symmetric space, it admits a biholomorphism onto a Siegel domain. A Siegel domain is an unbounded convex domain in complex Euclidean space, and which can be really a tube domain, sometimes a tube domain, or a little bit something more general than a tube domain, but still it's convex, unbounded, and the important thing is that the action of the group, of the real split solvable group NA, acts on the Siegel domain by affine transformations. And of course, NA acts simply transitively on G mod K and also on the Siegel domain, but on the Siegel domain, it is really affine. The action is by affine transformations. And an important, for instance, this biholomorphism in the case of the unit disk is just a Cayley transform that brings the unit disk onto the upper half plane. Or if we have the Siegel disk, we go into the Siegel upper half plane. It's the so-called Cayley transform. And under this map, phi, we have that, we just said that inside G mod K, there is this closed R-dimensional orbit, R, the orbit by this R copies of SL2R, let's say. And under these Cayley transformations, this R times X0 is really brought onto this, a true product of upper half planes. The product of these R upper half planes is itself, if you think, a tube domain. It's R to the R plus I times the positive, how do you say, the positive, the positive cone in R to the R. Not only, but the orbit of A, the orbit A times X0 is brought to by this biholomorphism phi onto I times the positive octant. Okay, okay. Okay. So we show an example, two examples. If we have, for instance, the unit ball in Cn, so we know that if n is equal to 1, we already said we have the unit disk that goes in the upper half in the upper half plane of C. If n is greater than 1, then this unbounded model is not a tube domain, but it is exactly this, for example. And then you see that these points of En, it is the imaginary part of Y1 minus this moduli square greater than 1, greater than 0. You see the points of the form Z1, comma 0, 0, 0 inside En are exactly a copy of the upper half plane in C. if we take the Ziegler upper half space of rank R, it means that we take the complex symmetric matrices of order R with the imaginary part positive definite. Then inside P we have something which is exactly the product of R copies of the upper half plane, and they are exactly these diagonal matrices, you know, with the imaginary part greater than 0. Okay. Okay. So this is for G mod K. Now we consider an N-invariant domain in G mod K. So what happens? So G mod K, we said it is biholomorphic to a Ziegler domain. And as a thick slice for G mod K, we had this product of R copies of the upper half plane, and which is a tube domain over the positive octant. So if we take an N-invariant domain in G mod K, this determines really a tube domain inside the product of these upper half planes, in the product of the upper half planes. So D, we can say it is N, the N action applied to this tube, how do you say, covers all D. So D determines a tube domain in the product of the R copies of the upper half plane, and vice versa. Now, if you take a tube in the product of the upper half planes and you apply N, you get an invariant domain in G mod K, in the Ziegler domain, and also in G mod K. Similarly, if we have an invariant function from D to R, this also determines a function from the base of this little tube associated to D into R, and conversely. So we have a one-to-one correspondence between N-invariant functions on D and functions on omega, no, F hat. And the regularity is also preserved. So these two objects that we associate to an invariant domain in G mod K are actually the ones that best express the properties of D. And they appear in the statements that generalized Bochner tube theorem in the case of standard tube domains. Okay, I don't know whether there are any questions so far. Okay. So now try to state the results about N-invariant domains in G mod K. So we have, so we take a non-compact irreducible Hermitian symmetric space of rank R, D, an N-invariant domain in G mod K, and then we call T this R-dimensional tube, which we associated to D. And we defined now this cone in R to the R, which is the positive octant in the non-tube case, and the positive octant intersected with the zero set of the last coordinate in the tube case. In general, no, when you have a Hermitian symmetric space of the non-compact type, we have that the Ziegler model is a tube domain when the restricted roots are reduced, and you have a non-tube model Siegel domain as a model when the restricted roots are non-reduced. So it's really clear who is who. So the first statement is that generalizes Bochner tube theorem is this: an invariant domain in G mod K is Stein if and only if the associated tube has a base omega which is convex and satisfies this additional property. This means that for every point x in omega, x plus the cone still has to be contained in omega. And the envelope of holomorphy of an invariant domain is univalent, so is schlicht. So the famous projection Q is injective. And so this envelope of holomorphy coincides with the smallest Stein domain containing D. So it means that it is the domain whose base omega is convex and satisfies this additional property. So you have to complete it and make it satisfying these two properties. So this shows that the tube domain associated to an N-invariant domain in G mod K is not an arbitrary tube in C to the R, but the second condition really tells us that this comes from a tube which is, that comes from a domain which is an invariant in G mod K. It's just not an arbitrary tube. Okay, so here we take an example. For instance, if we are in rank 2, this cone that I defined earlier in the non-tube case is just the positive octant, is R plus times R plus. No? It's the positive octant in R2. And in the tube case, instead, it is just R plus cross R, cross 0, sorry. So it is horizontal line, horizontal positive line. So in this case, we know that the base of this associated tube to G has to be convex and has to satisfy the second property. For every x in omega, x plus c has to sit in omega. So you see, in the tube case, we have that for every point in this region, omega, the yellow region, for every point, there must be the half line on the right. So you see, it cannot be just any convex set. It has to have this property. And in the non-tube case, again, we have a convex set, but you have this extra property. For every point, the cone, which is like a positive octant starting at x, no, with like x plus c, it has to be contained entirely in omega. So this is, so you cannot just take an ellipse. No, you have to take something with these properties. Okay. Now, I just say a couple of words about how to prove this. If we have an invariant domain and a symmetric Siegel domain, then you have to you show that it is Stein if and only if it is convex, if and only if omega, no, the base of the associated small tube, it is convex and satisfies this property. And in order to prove this, it takes some convexity arguments, but you need to embed the Siegel domain in the normal J algebra. So of course, it has some machinery behind. So you have this normal J algebra is just the Lie algebra of the real split solvable group A plus n. But of course, since it acts, the group acts simply transitively on the domain, this algebra inherits some properties from the domain. And so it's not that hard to prove this fact, but you have to embed the whole problem in this context. And but there is no classification needed and no boundary of the domain involved. So there is some machinery, of course. Okay. Okay, now the statement is about N-invariant functions on D. We have, for two domains, we have that there is a one-to-one correspondence between plurisubharmonic functions on D and convex functions on omega. In this case, if omega is the base of this R-dimensional tube associated to D, so we have that F, an invariant function, is plurisubharmonic if and only if the associated function F hat is convex and is decreasing on the half lines inside omega. So if omega, we said, if D is Stein, omega is convex. For every point, for instance, in the tube case, you have that the half line here, or this cone has to be inside omega. So along these half lines, or here also on the right, the function has to be decreasing. So it's not an it's not an arbitrary convex function, but there are additional conditions that come from the fact that this is the tube associated to an invariant domain, and an invariant domain in G mod K. Oh, vediamo un po'. Okay. So, given an invariant function, we are able to detect whether it is or not plurisubharmonic. Okay. Plurisubharmonic means that the complex Hessian is, when the function is smooth, for instance, says that the F is plurisubharmonic if the complex Hessian is positive semi-definite. So it means that in theory, you should have to compute the double derivatives, putting Z, I, Z bar, J, all kinds of derivatives. Anyway, using this this characterization of invariant and invariant plurisubharmonic functions, we can show that this function is an N-invariant potential of the Killing metric. The Killing metric is just the metric on G mod K, which at the base point coincides with the Killing form. And it is a multiple of the Bergman metric. So up to a constant, a real positive real constant, this function is, rho of n is a potential of the Bergman metric. And you see it's completely expressed in theoretical terms. In general, the Bergman metric is, the potential of the Bergman metric is the log of the Bergman kernel function that comes from the space of H2 functions, or L2 holomorphic functions, but here they don't appear. We just have a direct expression in terms of here this element is an element in G mod K, N, X at H is an element in A, K is the maximal compact, and B is the Killing form. So this is completely theoretical. And using this characterization of that we have about N-invariant plurisubharmonic functions, we can also show that all invariant potential of the Killing metric or the Bergman metric up to constant are this function in blue plus a real constant in the non-tube case, and they are given by rho plus this function C e to the AR plus D, where C and D are real constant in the tube case. So this AR, you see, is the earth coordinate of this element H in the Lie algebra A, in the Lie algebra of capital A, the group. So you have, so these are all the N-invariant potentials of the Killing or the Bergman metric, as you prefer. Let's see. Okay, so another thing is that if you have a scalar manifold with an action by a Lie group, and you have a G-invariant potential of the scalar metric, then you know that then this map mu f, you can construct the so-called moment map associated to f, which is defined as mu f of z, dc f in z, applied to an element of the algebra of G. So this map is a G equivariant and satisfies the properties of a moment map. And by this formulation, we can compute the moment map associated to rho, again, in the potential of the Killing metric, completely in Lie theoretical terms. You see, you have NAK, which is an element in G mod K. X is an element in the Lie algebra of N this time. And so you have this formula. Now, I maybe explain exactly all the terms, but it's a formula that gives the moment map, and with some computation, one can show that this moment map also coincides. It can be written like this: the Killing form applied to the adjoint n-1 of x. X is an element in the dual of n. The Killing form, and then add A. You see, A is the element, and of the A part of G, of G, yes. And Z0 is the element in the center of K that determines in the complex structure on G mod K. So the moment map can also be shown to be exactly this, and coincides with the restriction of the canonical moment map that goes from G mod K to G star. G is really the Lie algebra of G. And which is given by, here is the formula, mu, see, right, the formula on the bottom of the slide. This is the canonical moment map from G mod K to G star, where for canonical, we mean that it sends the base point into the look, the reference point should go into an element of the center of K, and if we choose that it goes exactly in the element of the center of K that determines the complex structure of of G mod K, then it's completely fixed. And the n moment map mu rho coincides exactly with this when we restrict it to n. Okay. So now we have, I wanted to say something about how to obtain this characterization of plurisubharmonic functions, because without computing the complex Hessian in coordinates, let's say. So we have D, our n-invariant domain. We have the function f, and then this Cayley transform inverse sends the base of the associated r-dimensional tube into D. So here is the correspondence between n-invariant functions on D and functions on omega. No? So you have f and hat f. So in order to compute the Levy form of a smooth n-invariant function, which, as I said, would be the complex Hessian, is determined by the complex Hessian. So you do the Hessian with respect to dz I, dz j bar. We don't want to do that. And so, why? Because the ordinary coordinates of a bounded of a domain in Cn are not aligned with the symmetries. So we want to compute this Levy form by computing this form ddcf using an identity which allow us to exploit the symmetries and avoid to do computations in coordinates. So if we have an n-invariant function on D, we define this and we fix an element in N, in the Lie algebra of N. We consider this function now become a function, is the x component of it's not yet a moment map, but it is a map that behaves like a moment map. This pointed out by Einsner in some paper. So you have mu x goes from D to R, and it is the contraction of DCF with the vector field induced by X. And this map is n-equivariant, and the differential of this function is, via this formula, minus the contraction with respect to X of DDCF. So we try to use these relations to compute DDCF. So, and we do it, since we do it not in coordinates, but using vector fields, and also vector fields induced by the n action, it means that sometimes when we do these derivatives, if the vector fields are tangent to the orbit, the derivatives are 0. So that helps a lot, and especially we avoid using the coordinates. So the computation of the Levy form or DDCF is reduced to a computation in with restricted roots. So no classification and no models. So that's maybe the nice thing about this method. Finally, let me see, maybe I have one more thing that I wanted to say. Can I proceed? not make it to get the last. What did I do? Let's see. Okay, no. Okay. I hope people see. This is that will be the last slide, I thought. So what I wanted to say that one can also obtain the characterization of N-invariant Stein domains by using the invariant plurisubharmonic functions, and which is actually curious is that also by this method you get the same shape of the base of the associated tube, which has to be convex, and this need to have this property that x omega plus the cone has to be contained in omega. And maybe I wanted to show what happens in the case of the ball. In the case of the ball, we had so the A orbit of the reference point was this red line, and the orbits were the oroballs or cycles. Here in rank 1, the orbits are of codimension 1. So the Stein domains has to sit either on one side or on the other. And the fact that the functions are decreasing when in the half lines in the cone tells us that the oroballs on the right-hand side of the orbit, those are the Stein invariant domains and not the other ones. So, okay, that was the last slide I wanted to show.
Yeah, well, thank you very much for a really interesting talk. Are there any questions?
I hope I was not too fast.
Any questions? It's really nice to sort of see how all the inaction really gives you so much. I found it really interesting. Any questions? Okay, if not, well, thank you again.
Yeah, I just want to say it was a nice talk. Thank you.
Yeah. And I wanted to mention say a little bit about upcoming talks. And oops, sorry, let me second here. So in 2 weeks, we have a talk by Fangyang Xing. And then in 4 weeks, on October 11th, we have a special lecture by Mike Eastwood in memory of Joseph Wolfe, who everyone may be aware of, passed away just a couple weeks ago.
No.
Yeah. And there will be time after that talk in 4 weeks for sharing memories, and we'll stay on Zoom and let people share. So